Okay, so welcome to a short video on how to perform or complete exam questions on level 2 acids and bases. This is just an old exam paper that I found with probably the most comprehensive question I could find. It's definitely quite tricky. So by going through these questions, I'll get an opportunity to illustrate some of the concepts that you would have learned in class and try to highlight some key ideas as we go. So it's just one entire question. Question 3 we're looking at. I'm going to use a different colored pen just to write in the answers. So the first question here is focusing on the fact that some species are weakly acidic and sometimes you have weak bases as well. So the key thing here is anytime you see reversible arrows, that immediately indicates that this species is a weak acid or base. Now in this case, this is a 3-carbon carboxylic acid, which is propanoic acid, if you remember from your organic chemistry. And with carboxylic acids, it's always the terminal hydrogen which is lost when it reacts with water. So the products of this reaction are going to be ethanoate, so C2H5COO minus, plus water as it gains that proton becomes H3O plus, which is known as the hydronium HY0N hydronium ion. Okay, so you have your products for the dissociation of that weak acid. So this is a weak acid with water. Other key terminology just with weak acids are as follows. So you always have a weak acid and a weak base. So this is the acid. The Bronsted-Lowry were two scientists who came up with a definition for an acid, and they said an acid is a proton donor, in which case the propanoic acid donates that proton to the water, and the species which accepts the proton is referred to as a Bronsted-Lowry base. So water is acting as a base in this case, and that extra hydrogen is added here to the water to form the hydronium ion. Now on the same note, on the product side, you also have species which could act as acids or bases. The ethanoate now could quite easily accept a proton back in the reverse process, so this is now referred to as the conjugate base, so it could act as a base, and because the water now has an extra proton which it could quite happily lose in the reverse direction, it's referred to as the conjugate acid. So in every time you write an equation for a weak acid or base which will have reversible arrows, you can also identify an acid, a base, the conjugate base on the right hand side, and the conjugate acid on the right hand side. So that's that first equation completed. The next equation is where we're looking at the ammonium ion. So this is ammonium, not to mix it up with the other species which is ammonia. So this is the ammonium ion. Could have come from the dissociation of an ionic compound like ammonium chloride. You put that stuff into water, and eventually this equation will happen where you form NH3 plus H3O plus. So again, we have a situation where we have a weak acid. Water is again acting as a base, though water can act as an acid, so it's described as being amphoteric. So amphoteric is just the word to describe how water can act as an acid or a base. So just be aware of that. There's one or two other species as well that can do that. So the ammonium reacts with the base, the water in this case, and the ammonium donates its proton to the water to form ammonia plus your hydronium ions. Again, the ammonia in this case is the conjugate. So the conjugate base, yes, could accept another proton. Lost my pen there. So the ammonia is the conjugate base again, and the water is the conjugate acid. Okay, so that's the first question. That would be an achieve type question, just to complete something simple like that. We move on to the next question now. They start to focus on testing if you guys know how to use the few equations that you need to memorize for level 2 acids and bases. And the three main equations you need to know for level 2 acids and bases, I'll just write them on the side here. Use a black pen. So you need to know the fact that the pH of a solution is equal to minus log to the base 10 of the concentration of hydronium ions present. That's the first equation you need to learn off. The second equation you need to know is that if you're given the concentration, or if you're given the pH, then 10 to the negative pH will give you the concentration of H3O plus. So that's the reverse version of the first equation. And the third equation you may have to use here is the relationship between Kw, which is the acid dissociation constant of water, and that's a number which you need to memorize. It's 1 times 10 to the minus 14. The relationship between that, the concentration of H3O plus, and the concentration of OH minus. And we just present that as a formula triangle, if we can, just on the side there. So they're the three formulas. Now I immediately write them down on my page. If this is my exam paper in November, I just get my paper and I quickly dump any equations that I need to know on the page, and then I can just use them later when I need to. So this table has the following requisites. The first situation we have is 0.0354 moles per liter of hydrochloric acid solution. It's a strong acid, it will fully dissociate, so we can assume that we will get this concentration of hydronium ions when that proton adds on to the water. So that's why the concentration of H3O plus isn't required, but we can write it in there anyway. It's 0.0354 moles per liter. Now the concentration of OH minus can be found. In this case, you cover the species that you're looking for. So we're looking for the OH minus, so we would cover that one with your hand, and it tells us to take 1 by 10 to the minus 14 and divide it by the 0.0354, and if you do that successfully on your calculator, then you should get an answer of 2.82 by 10 to the minus 13 moles per liter. Now a couple of things to point out here. Make sure that you can use your calculator to do pH calculations. This is a common error with students. They know what they're supposed to be entering in the calculator, but they can't actually use the calculator. It sounds ridiculous, but you'd be surprised out of a class of 30 how many people can't do that properly. Also, you need to present your final answer to 3 significant figures, and the units are up there, so we don't need to worry about that. The next line, we have to consider the pH. So we look back to the pH formula, and the pH formula says that we need to get to log to the base 10 of the concentration of H3O plus, which is this. So if you get minus log to the base 10 of 0.0354 moles per liter, you get a pH of 1.45, which makes sense because hydrochloric acid is a strong acid, and a strong acid should give you a very low pH. So that seems to make sense. So we'd be quite happy with that answer in our exam. We move on to the next situation. We have a strong base, so we're expecting a very high pH value for this answer. The first thing here now is they want the concentration of H3O plus. So in this instance, we have a concentration of OH minus. This is the concentration of OH minus that we would get if this species reacted with water, or dissociated in water. So to get the H3O plus in this instance, we take 1 by 10 to the minus 14, and we divide it by 4.27 by 10 to the minus 2, and your answer comes out as, 2.34 by 10 to the minus 13 moles per liter. And that's 3 significant figures again. That's really, you can see from that number, that's a tiny amount of H3O plus, as you'd expect when you have a strong base, whereas the concentration of H3O plus, just to compare that, is 4.27, a massive 4.27 by 10 to the minus 2. So that's much bigger than the concentration of H3O plus. And then for the pH, we have our concentration of H3O plus now, so we just get minus log to the base 10 of 2.34 by 10 to the minus 13, and that gives you a pH of 12.6, 3 significant figures, and that's a high pH as expected for a strong base. The final calculation here now is requiring us to use the third formula here. We're given the pH of 9.43, and if you want to work out the concentration of H3O plus, then it's 10 to the minus 9.43 using the second equation here, and that will give you an answer. If I just go to my other sheet here, that will give you an answer of 3.72 by 10 to the minus 10 moles per liter of hydronium ions. And to get the concentration of H3O plus, the concentration of OH minus, again you use your 1 by 10 to the minus 14, divided by this number here, and your answer becomes 2.69 by 10 to the minus 5 moles per liter of hydroxide ions. So this has a much higher concentration of H3O plus, much lower concentration of H3O plus and a higher concentration of OH minus, hence the pH is above 7. So everything makes sense there. We move on to the next part of the question. So that might have been for merit, to pick up a merit grade. Now part C and D, these are the real excellence parts of the question and shows real understanding of the difference between a strong acid and a weak acid, or a strong base and a weak base. Okay, so as I say, this question is about determining if you guys understand the difference between a strong acid and a weak acid, or a strong base and a weak base. So we have to look at the 4 species we've been given, place the following solutions in order of increasing pH by writing them into the boxes below. Now I may not be able to write the final answers in the boxes below just yet. I might have to work through some calculations and reasoning with equations before I can make that final judgment. But just on initial inspection, stand out straight away is sulfuric acid is a very strong acid. So that's a strong acid, so I'm just going to use SA for that. It's also diprotic, and I'll come back to that when I talk about its equation. But it's a diprotic acid, so it's very strong. Sodium hydroxide is a strong base. Alright. Now, hopefully you guys can tell the difference between having 0.01 moles per liter and a 10 times more concentrated solution of 0.1 moles per liter sodium hydroxide. So this is a strong base in both cases, but this one is a higher concentration. So we know that the pH of the 0.1 mole per liter will be higher than the pH of the 0.01 mole per liter. Now this here is ethanoate, and that is also weakly. That's a weak base. Okay, so you need to know a couple of weak bases need to be memorized for your assessment. They love asking about ethanoate reacting with water. Often you have to write 2 equations, and we'll talk about that as we write the equations for it. But it's weakly basic, so the main decision is going to have to be made between these two here, the ethanoate and the sodium hydroxide. Okay, let's just save some power. Hopefully we get through this. Okay, so the next thing we need to talk about is the equations for each of these situations. So the first place anyway we're saying is sulfuric acid, H2SO4. If you write the equation for sulfuric acid reacting with water, it's H2SO4. And we have a complete arrow because it's a strong acid, so a complete arrow. And then we get 2 moles of hydronium ions, and then you get your sulfate, which is a spectator. So as a result of this type of acid is referred to as being a diprotic, di meaning 2, protic coming from proton, so a diprotic acid. And as a result, even though the starting concentration of H3O plus is equal to 0.1 moles per liter, so that's the concentration right there. Starting concentration of H2SO4 rather is equal to 0.1 moles per liter. So from that 0.1 mole per liter, you'll end up with 2 times that concentration of H3O plus. You'll end up with a concentration of 0.2 moles per liter of H3O plus. And if you get minus log to the base 10 of 0.2, you'll get a pH of 0.7, which is very low. And hence we can put that first in our box definitely. So sulfuric acid is going to have the lowest pH. The next situation is we look at the other end of the spectrum. So if we look at last place is going to be our 0.1 mole per liter of sodium hydroxide. So let's just separate this out. So the sodium hydroxide, let's do that in a blue. So in this instance, the concentration of H3O plus needs to be established from that. So that's going to be equal to 1 by 10 to the minus 14 divided by the concentration of hydroxide ions that you get from the dissociation of sodium hydroxide, which is 0.1 mole per liter. And that will give you a concentration of H3O plus of 1 by 10 to the minus 13 moles per liter. which gives you a pH of 13, which is very high. Very high. So we can put in our 0.1 mole per liter sodium hydroxide right here with the highest pH. So now we just need to decide, as I say, between the ethanoate and the 0.01 moles per liter sodium hydroxide. So if I just go and take a new page here, and if we talk about ethanoate, CH3COO minus first versus, so it's the same concentration of both. So 0.01 moles per liter of ethanoate versus 0.01 moles per liter of sodium hydroxide. Okay, so with ethanoate, what you've going on is the ethanoate ion acts as a base and accepts a proton from water. So in this case, water is acting as an acid, whereas before we saw it acting as a base, and this is the amphoteric nature of water. We have reversible arrows because it's a weak base, and propanoic acid. Keep referring to this as ethanoate. This is propanoate. It is ethanoate. There's only 2 carbons. So ethanoic acid in this case. Now that situation is versus sodium hydroxide, and if sodium hydroxide dissociates in water, the situation you have there is it's complete dissociation. You get your sodium spectator ion, you get water forming again, but you also get the production of OH minus ions. So in both cases you get the production of OH minus ions. So we have to decide which species is going to produce the most OH minus. Now the key to this, answering this question, is really all to do with the type of arrow that is being used. Because this arrow shows complete dissociation, which is what happens with a strong base, whereas this arrow here for a weak base shows partial dissociation. And because it's partial dissociation, the equilibrium actually favors the left-hand side. And therefore you don't, the one thing you're definite of is you don't get 0.01 moles per liter of your OH minus ions from the dissociation. You don't get that. That much is definite. Whereas you do know over here that you do get the full 0.01 moles per liter of the hydroxide ions, because the sodium hydroxide completely dissociates. So without having to do any calculations, because you guys haven't been taught how to work out the pH of a weak base yet, so without having to do any calculations, you can clearly rank the ethanoate as having the lower pH, because it favors the less production of OH minus ions. Therefore it's in favor of the more acidic pHs. So if we go back to our answer right here, we're going to put our ethanoate H3CO minus right there, and in this case it's our sodium hydroxide, which was 0.01 moles per liter. And that's how you answer that question. So that's a great question. Haven't seen many like it now in previous years. So that really tests your understanding of a weak base versus a strong base. And then a strong acid is thrown in there as well. The next part of the question, and this is the final thing I'll cover today, is this idea of conductivity, electrical conductivity, and ionic compounds. Anytime you put an ionic compound into solution, you release ions, and those ions can act as charge carriers. So the essence of this question is, the more charge carriers you have, the better the electrical conductivity of the solution formed by that species. So here's the question. The table on the right hand side gives the pH values of 3.1 mole per liter solutions. So the concentrations are all the same. Place the 3 solutions in order of increasing electrical conductivity by writing them into the boxes below. So you've hydrochloric acid. Automatically we know that's a strong acid. Full dissociation. Calcium chloride is an ionic solid. Or if we're forming a solution, then it would be an ionic solution. And HOCl, or hydrochloric acid, is a weak. And you can tell it's a weak acid from its pH relative to the hydrochloric acid. So you're not expected to memorize these things, but it's nice to know a few. Calcium chloride, like all salty solutions, are neutral. All right. So you have those three species to consider, and the question asks you to justify the order in terms of particles present, so that's going to be the ions in this case, and concentration of particles linked to the electrical conductivity of the solution. You should include equations in your answer. So if they say that, then you must be writing equations. Sounds obvious, but it's surprising that many students won't do that. So let's take a look at the answer for this one. So conductivity, I just wrote some quick notes down here, but for conductivity, let's start off with the one with the highest electrical conductivity can be determined by simple equations. Let's just ignore that. So the first situation we have is we have HCl reacting with water, dissociating in water, whatever way you want to look at it, complete dissociation, and you're going to get chloride ions plus H3O+. So for the full dissociation of HCl, our starting concentration was 0.1 moles per liter. Alright, we're going to get 0.1 moles per liter of HCl ions plus 0.1 moles per liter of H3O+ ions, which gives us a total ion amount of 0.2 moles per liter of ions. Alright, so that's the concentration of ions we'll get from the full dissociation of HCl. That'll account for quite good electrical conductivity. Let's take a look at HOCl then. Hypochlorous acid will dissociate partially with water to form H. We'll just put the OCl minus first, so the hypochlorite ion plus H3O+. This does not, we cannot just say that if we start off with 0.1 mole per liter of hypochlorous acid that we're going to get exactly that amount of these two species right here, because it's only partially dissociating. So we can't make that assumption. The only thing we can be definite of is that it's going to be less than 0.2 moles per liter because of this reverse process taking away from that production. And then the final species to look at then is the calcium chloride. That's written quite poorly. Calcium chloride plus H2O. So let's just write water above it, because what we're really talking about here is the dissociation of calcium chloride solid in water, and you'll get Ca2+ ions aqueous plus 2 Cl- ions aqueous. So the key point here is that if you start off with 0.1 mole per liter of calcium chloride, and then it fully dissociates, you're going to get 0.1 moles per liter of calcium 2+ ions, and you're going to get 2 times that concentration of chloride ions. So in total you get 0.3 moles per liter of ions. So hopefully it's obvious after doing those little calculations. I shouldn't need to write down the explanations, but if you have 0.2 moles per liter of ions for the HCl, if you've 0.3 moles per liter of ions, where did that disappear to? That was spooky. If you've 0.3 moles per liter of ions for the dissociation of the calcium chloride, and you have less than 0.2 moles per liter for the hypochlorous acid, then in terms of ranking these species in terms of conductivity, the lowest is going to be the HOCl, hypochlorous acid. The middle species is going to be the HCl, and the highest is going to be the CaCl2. Okay, so that I'm pretty happy with that exam paper, because I have my little revision chart in front of me, and that question really reviews everything you need to know for level 2 acids and bases. The only things they can change around might be the species they talk about and the different numbers that they give you for your calculations, but otherwise that question is really comprehensive in covering all the concepts you need to know.